Dear Clio community, my name is Robert Riedel and I'm CEO and co-founder of a Germany-based laser company, Class 5 Photonics. At Class 5 Photonics, we build the most powerful femtosecond lasers available on the market, and it's a great pleasure to introduce our high-power OPCPAs at 2-micron wavelengths with scalability to 100 watt average power here at the Virtual Clio. And I will also give a sneak peek to our first commercial XUV source at the end of the talk. The motivation behind longer laser wavelengths is clearly the extended cutoff of frequency of high harmonic generation, reaching into the soft X-ray regime. I chose this famous publication here from Tino Popmenchev, who nicely demonstrated this cutoff extension by using different lasers. We see normalized high harmonic generation spectra plotted over photon energy in kilo electron volts. In particular, we see that driven by 2000 nanometers, the harmonics nicely cover the water window between 200 and 500, 600 eV. So exactly here, Class 5 has the plan to deliver the most powerful carrier envelope stable few cycle pulses. At Class 5, we address those technological challenges with a skilled team of ultrafast experts and with international research cooperations that range from Asia to the US and Europe, of course. Our project leaders and engineers come from renowned groups in attosecond physics, from free electron lasers, and from high-field terahertz generation. And we believe that that really makes a difference in solving our customers' needs who are performing cutting-edge research with our high-power sources. And our key references speak for themselves. We delivered systems to Stanford, SLAC, Berkeley, Harvard, Columbia, and many other high-class universities and research facilities in the United States, Europe, and Asia. Let me introduce the key principle of our super high-power OPCPA system that we call Supernova. It's pumped by a kilowatt picosecond laser, and that consists of 3 modules, a 400 watt preamplifier, a 1000 watt main amplifier, and compressor, bringing the pulses down to about 1 to 1.5 picoseconds. And here nicely in the front, you see our high power OPCPA system. Let's have a more detailed look on the schematic design of the OPCPA system itself. Here we show a 1.5 to 2 micron high power tunable OPCPA. The pump laser uses, first of all, a 35 watt fiber laser from Amplitude as a front end, and about 20 watt of those uncompressed power are used to seed this InnoSlab kilowatt amplifier provided by Amphos. 15 watts compressed are used to drive the preamplifier section of the OPCPA system. The preamplifier section itself consists of a white light generation module and a difference frequency generation module, and a first non-collinear OPCPA that's based on KTA and is used to generate 6 microjoules of seed energy at 1.5 to 2 micron. The pulses are stretched in a 20 millimeter long silicon, bulk silicon, to match the main pump pulse duration of about 0.6 picoseconds. The main OPCPA here is a single KTA crystal pumped by 6 millijoules at 100 kilowatt, which is exactly 640 watts, to be clear. And the output energy exceeds 1 millijoule at 1.75 micrometers central wavelengths. For the final compression here, we use an array of specially designed chirp mirrors that are optimized for the wavelengths range between 1.4 and 1.7 micron. A powerful feature of OPCPA in general, and especially this system, is the ability to tune the central wavelengths. So here we show a measurement of the amplified signal spectrum after the high power stage, published by Matt Windler from SLAC using a Supernova OPCPA. Stable amplification has been achieved between 1.5 micron all over to 2 micron. The highest energy and average power here has been achieved at 1.75 micron, as you can see, 105 watts. This corresponds to 16% pump to signal conversion efficiency. A gain factor of up to 2 times is expected by adding a second amplifier at this stage pumped by the exceeding power or the residual power of the main pump here. At shorter wavelengths here, towards 1.6, 1.5 micron, strong idler absorption prevents higher gain. So we have here only 60 watts of power at 1.55 micron and even less power at exactly 1.5 micron. And as you can see here, at 2 micron, we reach 60 watt of average power. But giving the whole range, this OPCPA system demonstrates the highest average power ever demonstrated in an OPCPA, especially pumped at those high power levels. The shortest pulse has been achieved at 1.65 micron. You can see the autocorrelation here on the right. 85 watts of average power have been achieved at 1.65 micron, and accordingly this slide shows here the amplified spectrum presented in blue. Now, having demonstrated the ability to use a kilowatt pump laser and OPCPAs to reach this 100 watt regime, we took the opportunity to develop a broadband 2 micron system with pulse durations in the few cycle regime. So let's have a look on that. This system here is designed for the generation of water window attosecond pulses as motivated in the introduction of my talk. Again, here we use the kilowatt pump laser, at this time at a 50 kilohertz repetition rate and 16 millijoules of pulse energy after the compressor. In the shown configuration, the pump laser has a 30 microjoule auxiliary output that drives the DFG seeder, quite similar as before. The main difference of the DFG seeder is the enormous spectral bandwidth that we can achieve, supporting sub 20 femtosecond pulses centered at 2 micron. And the OPCPA preamplifier here is pumped now not by this auxiliary output, but already directly by a 0.5 millijoule fraction of the main pump output, yielding 30 microjoules of seed energy for the OPCPA main amplifier. Also here, bulk silicon serves as a stretching material. In the currently achieved configuration, we have successfully reached about 1 millijoule of broadband pulses at 2 micron, here 0.95 millijoules, using 60 millijoules as a pump. The conversion efficiency in this particular configuration is mainly limited by nonlinearities due to the high pump intensities of the picosecond pump. So changing the configuration, which is currently the case, and further will enable further gain above 1.6 millijoules at the output, and that's especially expected by implementing a third OPCPA stage here that shares the output power of this pump laser. The pulse compression is achieved by, again, by a chirp mirror array, which is designed in this time for the wavelength range covering more 1.75 to 1.4 microns, so quite broadband. Please note, we see this is quite an advantage, that this system has no active phase shapers, such as an SLM or a Dazzler, that would be required for compression. It's a purely passively compressed system, and we have done this type of compression before, also in the past. That approach strongly reduces the complexity of the whole laser system. Let's have a look on the amplified spectrum from OPCPA2. You see that at full power, which is about 50 watts in the moment, we measure a spectrum that supports a Fourier pulse duration, a Fourier limited pulse duration of 23 femtoseconds for with half maximum, which is very close to the few cycle regime. Because the chirp mirror compressor is currently being set up together with a two-stage, like with a three-stage OPCPA approach for even higher power, we have verified the compressibility and phase by Frog measurements using pure bulk silicon as a compression material. We achieved a pulse duration of already 41 femtoseconds through with F maximum, as you can see here in the retrieval. And as expected, the residual higher order dispersion introduces pre-pulses and a little post-pulse here. But again, this is only by compression, and the future chirp mirror compressor will eliminate also the higher order dispersion here and allow for high fidelity pulses with pulse durations well below 30 femtoseconds. I would like to reference to our works around 1.5 micron, where we show a very nice compression profile with purely passive chipper compression. Eventually, this laser system is going to be the highest average power 2 micron fuse cycle laser that has ever been realized. And future steps of this particular system are really the power scalability and the measurement and control of the stable carrier envelope phase. Let me take the opportunity for the last part of my talk to focus on the unprecedented flexibility of OPCPA in general to realize powerful multicolor pump probe systems spanning from the mid-IR to the extreme ultraviolet. Those systems are concepted for advanced spectroscopic techniques. Schematically, we share the same pump laser here to drive two individually tunable OPCPAs. The pump arm can be in the infrared range up to about 10 micron, for example, this example gives an 8 micrometers infrared wavelengths with a 100 femtoseconds bandwidth. And the probe arm can be used to drive our commercial XUV high harmonic generation source. So this system is ideal for advanced photoelectron emission experiments in solids such as RPIS and PIMS, reaching a decent flux of 10 to the 13 photons per second and spectral resolution of 80 millielectron volts. This system can resolve details in electronic band structure while keeping a great time resolution here around 30 to 50 femtoseconds. Let's have a quick look on the DFG. Here we present our first preliminary results. This is a high power 8 micron OPCPA delivering 2 microjoules at 200 kilohertz repetition rate. And this spectral bandwidth here supports already sub 100 femtoseconds, which is great for an 8 micron wavelength pulse. For the high resolution XUV source, just very briefly, we focus the second harmonic of the driver beam here at 800 nanometers, so we get the 400 nanometers into a krypton gas jet using a tunable OPCPA. And that concept has been introduced by the group of Robert Kindle in Berkeley, who is now at Arizona State University in Phoenix. In this work, this second harmonic driver concept is combined with a thin tin metal filter. The transmission is shown here, and this is the position of the harmonics. Basically, here you can see the measured harmonics. In order to isolate a single harmonic around 22 eV at very high transmission. So this is not the end of the story. We are currently working on an even more advanced concept that allows for not only sub 80 milli eV, but sub 20 milli eV resolution while still keeping femtosecond scale time resolution. So stay tuned for the news on the next conferences. At this point, I would like to conclude my talk about high power OPCPAs at 1.5 to 2.4 micron. First of all, we have demonstrated 100 watt average power at 1.75 micron wavelengths using kilowatt pumped OPCPAs. This is the highest power OPCPA ever demonstrated in this wavelength range and in any wavelength range at all. Secondly, we have achieved already 47.5 watts of output power and 40 femtoseconds at 2 micron to be scaled 2 watts to 20 femtosecond range and towards 100 watts of output power as well. Secondly, I gave an output over multicolor pump probe systems at 8 micron OPCPA, which are commercially available at class 5. And we have various options using the full range, the full toolbox of OPCPA. And fourth, I presented a high flux XUV source centered at 22 eV with 10 to the 13 photons per second. The future. We will demonstrate soon to reach the spectral resolution of 20 milli eV at 22 electron volts. And we extend our HHG concept towards the water window using the presented sources here, centered at 2 micron OPCPAs. Thank you very much for your attention. And the talk is open for the discussion.